we are very happy to have Edward Mazenc telling us about strings from Feynman diagrams.
You couldn't not have me, unfortunately. Okay, so I want to tell you today about some work, a bit of a program over the last 2 years with Rajesh Gopakumar, and some ongoing work with multiple people here, so Matthias, Shoda, and these are 2 graduate students of Rajesh. So I'll start by turning back the clock almost 50 years, which turns out to be almost simpler than solving confinement. And I want to show you here, these are 2 pictures taken from the very first paper of what became the 'Hooft expansion. Okay? And 'Hooft had an idea that somehow these gauge theories might admit some sort of string description, not thinking so much of the flux tube picture that we've talked about a lot recently, but thinking about perturbative gauge theories. Okay, so starting around a free gauge theory and thinking about, in perturbation theory, the Feynman diagrams of the gauge theory. In particular, what he showed is that the power of n, sort of the weight with n of each Feynman diagram, was given by the genus of the Feynman diagram. So the idea was that the 1 over n expansion is some sort of topological expansion of some hopeful 2D string theory that pops out. Okay? But the idea as to how this picture might truly be concretely realized, how do you go from a sum of Feynman diagrams to some sort of sum over 2D surfaces embedded in some space, is maybe still a bit suggestive. Okay? So what I want to do today is to find a concrete example where we're going to actually make some simplifications, obviously, to make any progress. So if you thought 2 plus 1 or 1 plus 1 was low-dimensional gauge theory, you're in for a treat today, because we're going to be doing 0 plus 0-dimensional gauge theories. Okay? So the gauge theories I'm going to be considering today are just simple matrix integrals. Okay? These are integrals like this. This is what I call the simplest gauge theory. Over 2 Hermitian matrices, K and M, they're n by n. And the potential, if you want the action, is as simple as you could possibly imagine. At least you have to write down one of the matrices each. Okay? And if you want, you would have some 'Hooft expansion by having some sort of interacting potential. But I want to think today about all of those interactions perturbatively around the free point. Okay? So what we're going to be doing is really just studying what I think arguably is the stupidest matrix integral you could do. Okay? And if you want, what's going to make our life easy is that when we look at these Feynman diagrams here of 'Hooft, we're essentially just setting all the propagators to 1. Okay? But the challenge as to how these graphs become 2D surfaces is still there. Okay? So that's the sense in which I think it's a toy model, but it's going to teach us something. So I'll try to start out with just the main result. Okay? So the main result is going to be identifying the gauge invariant observables here, and to all orders in 1 over n. Okay? So we're going to start with just traces. Trace a k to the lj. J goes from 1 to the big L. Traces of m and I. Okay. And I'm going to imagine taking this correlator and expanding this in a power series in 1 over n. Okay? And so it'll have some coefficient n to the 2 minus 2g. So that's what this g is going to be. This is a connected correlator. And what this is going to be computed by a dual string theory, which if you want, we're trying to derive today from the Feynman diagrams. So on this side, this is going to be an L plus L prime point function. Okay, so I'll call these Lj. So there'll be 2 sets of natural vertex operators. And this will be computed on a path integral by summing over 2D surfaces of that particular genus G. Okay? And of course, I'm going to tell you what worldsheet theory that we're computing that in later. Okay, any questions just about the statement? So this is true for every order in 1 over n. It's not just a large n statement. Okay, main result is clear? Good. Okay. So you might be wondering what could possibly be new to learn about matrix integrals and strings, since we've been doing this in many ways for 30 years. And if you want, the first wave came in the 90s, where we started already thinking about implementing this program. And the picture there was that somehow what you needed were some very, very dense Feynman diagrams. And the way that you should think of the relationship between the Feynman diagram and the surface is some sort of latticization or a discretization of the 2D surface. And what you had to do to get a sort of genuine string theory with nice, smooth, continuum surfaces is you had to take a further limit, which was called the double scaling limit on the matrix model. some sort of continuum limit on the world sheet. So the big conceptual thing today is that we're not doing a double scaling limit. And the reason why is because if we want to understand something the way like ADS-CFT might work, there is no such double scaling limit. So if this Hooft picture is supposed to be also somehow a guiding post for us in the way, say, the dual to n equals 4 superbeing Mills works, we need to work in the conventional Hooft limit. And that's what we're going to be doing today. Okay? So in particular, we're going to be looking at very, very sparse Feynman diagrams just to really try to make a point. Okay, if there's one thing to take away from today's talk, it's sort of the following slogan, is that we're going to think of each single Feynman diagram as a worldsheet. Okay?
Yeah, I think the Kancevich matrix model had similar philosophy.
It has a similar philosophy, and in fact, we're going to be using a lot of tools from that. Secretly, there's a double scaling involved, but I can try to explain that outside. Good.
Also, why are you not considering the operators like trace, KM, KM?
So, great. So you might have thought just the most general operators are going to be the words. So traces built out of multiple of the Ks and the Ms inside. That's a very normal thing to do. It turns out, so one of the reasons we're studying this is that it actually computes operators, or certain correlation functions in a topological subsector of n equals 4 superbeing Mills. And these K and M's are actually operators at different points. So when we build single trace operators, we want to look at single trace local operators in the gauge theory. So we don't mix the K's and the M's. That's why. Okay.
So I can imagine them as Z and Z bar, K and M's.
Yes. So for us, these are going to turn out to be some combination of fields in the chiral algebra of n equals 4. But you could also think of Z and Z bar, and a lot of the story would go the same way. Okay. Yeah, does that answer your question? Yeah.
Very naive one. Just I don't remember the exact difference between the double scaling and Hooft. What parameter is scaling differently here?
Good. So here at Hooft, we're taking n large if you want, okay, but not strictly infinite. In the double scaling limit, you're taking n strictly infinite, but you're keeping some other coupling as it's going to some sort of critical coupling. And you're keeping a product of that fixed, okay? But it's not the conventional Hooft limit.
That's not how I would say.
Oh yeah, how did you say?
I thought it's a Hooft limit where you also send Hooft coupling to.
But the genus, yeah. But maybe the way I'd say it's different is that the genus expansion, or what's G string, is not 1 over n. So today G string is going to be literally 1 over n. And the genus expansion is just going to be the 1 over expansion.
Should there be a second parameter that's going small, or what's the second parameter that goes with n to generate something?
No, so right now we're just starting at 0 Hooft coupling if you want. Yeah. So if you wanted to consider, we would write something like lambda trace k to the 4. And then we do theory in that lambda. Okay, good. So there's two things I need to do. First, I need to tell you, if we're not going to work in this double scaling limit, I need to give you a new picture as to how the Feynman diagrams are reconstructing these 2D surfaces. And then also what I'll need to tell you is what is the string theory as we step away from this limit. Okay, so I'll try to distill down those two lessons here. So let's start with this. So how are we essentially going to very precisely translate between gauge theory Feynman diagrams and 2D worldsheets? So the idea is to use something that's called, this is quite modern math, so this is late 80s. It's called the Strabel parametrization of the moduli space Riemann surfaces of genus G with n marked points. That's where you would essentially insert your vertex operators. And n extra positive numbers, r plus n. Okay. And what this is an exact equivalence between what we call metrized ribbon graphs. So these are just the gauge theory Feynman diagrams. But with a little extra information, is that I'm going to assign to every edge of the diagram a particular number, a positive number that I'll call the length. Metrized ribbon graph. And what this is equal to is a point on this MDN times r plus n. Okay. So a point there is really some sort of worldsheet. Now, there's a few more things I should tell you a bit about how this dictionary works. I'm assuming most people haven't seen this before, but this is indeed how the Confining Strings works. We can associate a genus here by v minus e plus f. This would be 2 minus 2g. That's the g that I'll associate here. So in this case, g is equal to 0. And over here, that will be the genus of the world sheet. Okay. Another entry in our dictionary over here is that the number of faces is equal to n, the number of marked points, or the number of closed string insertions. So over here, what I'm showing you, for example, is a genus 0 4-point function. This is just a 4-point function on the sphere. So we have 1, 2, 3, 4 marked points. And that corresponds to the 4 faces here. 1, 2, 3, and 4. Now, of course, over here, there's continuous moduli on these world sheets, right? So like the tau and tau bar of the torus. So how is that encoded over here? So if you want the coordinates on moduli space, this is exactly what these lengths are doing. If you want, you should think of the lengths associated to each edge as coordinates on moduli space and telling you which world sheet we're talking about in particular. Okay. Any questions about here?
I think naively I would have assigned, what is it, the insertions and the vertices.
Good, so that's going to be an important part of the discussion today. Yeah.
Okay.
This is at least how the Strabel construction works.
And then the r to the n, r plus, those are n. I thought n was the number of vertices, but it's,
So
sorry, yeah.
n is the number of marked points, and here it's the number of faces. Okay. So in particular, let me try to explain what these n positive numbers are. These n positive numbers are the sum of the lengths around each faces. Okay, that's what they are. Ultimately, what it's going to be is essentially the length of the closed string state, of the asymptotic closed string that you're creating. So this might look a bit like a bunch of math mumbo jumbo. So let me try to paint a bit of a physical picture as to what this is. So the way you should think of this whole Strabel construction is a very smart choice of gauge on the world sheet, right? So a point on MGN is not telling you about a metric yet, right? A point on MGM is a surface with a choice of metric mod diff cross file. Okay? So if you want, I have a choice to choose a metric. The metric I'm choosing is this very particular metric called the Strabel metric. And in this gauge, if you want, it's going to make manifest the correspondence with the Feynman diagrams. Okay? And so how does it do that? So first of all, what I'm doing here, if you want, I'm just taking this graph, and I'm going to draw it on top of this 4-point function. This is the same graph, and if you want, this is just, these have been conformally mapped to marked points here. Okay, but that's these same 4 faces. And what it does, if you want, is that it decomposes the world sheet as a bunch of half cylinders, half infinite cylinders, okay, glued along this graph, which is called the Strabel graph. Okay, so you just take these cylinders and you glue them, and there's very precise gluing rules. What it actually does a bit more, and I think particularly for integrability people this might be a little interesting, is that it actually decomposes the world sheet as a collection of strips. And these strips, ultimately, I want to think of as the world sheet of open strings. So this is telling you how to sort of glue the world sheets of open strings together to create the closed string. So let me try to show you where these strips are. Above each edge, we associate one strip. Okay? So for example, here, there's one strip. So how is this closed string built? So there's one strip above this edge. There's another one over here. Okay, oops, it's a bit bad in the diagram. So I've done better here. So this is a cylinder, if you want, built out of 4 separate strips that have been glued together. And if you want, what this also provides is a sort of covariant, kind of natural string bit picture. Because what you can see is that the closed string is really created by these 4 different bits. Okay? And each strip is the world sheet of that string bit, if you want. Good. So halfway through, the hardest part is done. Okay. So the next thing I need to tell you is, well, what are the world sheets that we're actually deriving from these gauge theories? Okay? What if you want is going to replace what was known as the minimal strings in this now Hooft limit, not the double scaling limit. So if you want, we've started kind of from the stupidest gauge theories. So we're gonna get the stupidest string theories out of them. And so A is an A model topological string. Okay. If you want, this is going to be just a kind of a topological version of some Wess-Sumino-Witten model with this target SL2R mod U1. And it appears at this very special supersymmetric level. This is ringing some bells. You might have seen this actually in the derivation of the ADS3-CFT2 correspondence for the dual of the symmetric orbital. And if you want, this is some topological version with an extra coset hanging in there. Okay? And here, if you want, something like trace m to the k is going to create some vertex operators, vk, that were studied already in this theory. And what's important about this theory is that it localizes to certain covering maps of a sphere. And what these VKs do is they introduce some branching in the way that the world sheet wraps some target space. Okay? So we're going to spell that out. Okay. Now B is for B model. Okay. So if you want, this is something related. It's an equivalent description. So all three of these are equivalent rewrites of the same closed string theory. And here, if you want, telling me sort of what the potential of the matrix model is equivalent to specifying some superpotential, Landau-Ginzburg superpotential on the world sheet. So in this case, it turns out to be very simple. It's just 1 over z. And C is for C equals to 1. I might have done that on purpose. Yeah. Okay. So the C equals 1 string. And what this is, it's at self-dual radius. So this is a compact boson, compactified at the self-dual radius, plus C equals 25 Liouville. And here we have something very simple, that these trace m to the k's are the very natural operators in the C equals 1 theory, negative momentum tachyons. And this k of the trace is labeling the momentum of the tachyon operator. And for example, trace k to the n, k to the k always feels a little wrong, t plus n. So those are these two matrices correspond to the positive and negative momentum tachyons. And for example, what we've done is, well, we've shown this is true to all orders in 1 over n, so to all orders in the genus expansion. But just for sanity, we, for example, checked some correlators up to genus 3 and checked with some results that you had from the 90s. And they agree. So this is a very satisfying thing. Okay, so all of this, quite general. So if you're anything like me, you might need an example to kind of wrap your head around this. So what we're going to do is look at, if you want, the simplest Feynman diagram in the simplest gauge theory, okay? And in particular, I'd like to draw your attention to the fact that it's in no way sparse. Okay. So this is going to be a planar 4-point function of very simple operators. Trace m squared, trace m squared, trace k squared, trace k squared. So how do I draw that as a Feynman diagram? Well, I have 4 external vertices for each of the single traces. And the number, the valency of the vertex is just the power of in this trace. Okay? So what we want to do is we want to first go from this diagram and we want to reconstruct the world sheet. And over here, what we're going to do is we're going to understand how the diagram actually knows even how to embed the world sheet into the target space. Okay? It knows how to take this 2D surface and put it in like the equivalent of the ADS. But let's start with the world sheet. So what we first want to do is to go from this diagram to this Riemann surface. So how are we going to do that? And this is related to your question. So here we have 4 vertices, and we want this to become a 4-point function. Okay. In this Stribble thing I was telling you over here, I told you that there are as many faces as there are marked points. So what do we have to do, right? Here there's only 2 faces. So what do? We take the dual graph. Okay. So I'm going to draw the dual graph. Dual graph will look something like this. Okay, just crosses the edges. And let me try to draw this Stribble graph over here as well. So it'll kind of go around. Okay, so the first thing to take away is that the Stribble graph is actually dual to the Feynman diagram. So Stribble graph is the dual to the Feynman diagram. So it's a little small for the people in the back, but yeah. Okay. Now, what I was telling you over here is that we need not just the graph, right? That's just some discrete information. What I need to do for the coordinates on moduli space is I need to assign these lengths to the edges, okay? So this is a bit of an art, and we've tried several things, but this is the one that seems to work. We can ask, what is the length assignment, okay? So the lengths that we're going to associate to each of these edges is going to be the number of wick contractions between the vertices that it's crossing. Okay? So in this case, it's just crossing a single wick contraction. So I'll assign this length 1, and then a single length contraction, 1, 1, 1. Okay? So if I had, for example, multiple wick contractions here, say I had 3 wick contractions, because I had some other correlator, I would have assigned length 3 here. Is that clear to everyone? So now is an important part. If these lengths are just the number of wick contractions that it crosses, the number of dual edges, this is always going to be an integer. Okay? This is always an integer. So what's happening? Okay? Remember that once I have this stable graph and I have the lengths, I have a unique point on moduli space. Okay? A unique world sheet that I'm specifying. So what's going to happen is that all of the world sheets are just going to be labeled by integer numbers. Okay? So what I've done, if you want, I've latticized not the world sheet, but I've somehow directly discretized the moduli space directly. That's maybe the conceptual novelty here to think about. Now, I was telling you that there's something about we're gluing a bunch of strips together, so let me try to show how that works. And I think what's quite satisfying is that the strips turn out to just be the edges of the Feynman diagram. Okay? So you should really think of, say, the I and J indices, the color indices that are flowing in here. What these edges are, if you want, the ribbons of Hooft's picture, are really the world sheets of some strings ending on the I and J fibrine. Okay? So let me try to identify these. So I'll try to use some colors here. So I want to show you that this guy is essentially built out of 4 different strips. So where are the strips going to be? So I'm going to draw the following lines like this. So let's look at this diamond shape, and we're going to find it over here. So these 2 vertices are over here. Okay. So if you want, you have this. So if you want, there's essentially something like this going on. So there's one quarter here, there's another quarter here, another quarter here, another quarter here, and they all come together to glued together to create that 4-point function. Okay, is that clear? And each one of these quarters is exactly just one of these strips. Okay, so every edge of the Feynman diagram is one of the strips that make up the world sheet. Good. So you can imagine you take some correlator, and so we have some observable here, and we'll write it as a sum over Feynman diagrams, say of some particular genus, and each Feynman diagram is 1 point on moduli space by this construction. It's one world sheet. So what we're doing is we're essentially filling up the moduli space with these very discrete points. Now at this point, you should tell me, Edward, you're totally crazy. What string theory? Well, that's true, but what string theory could possibly do something like this? What would somehow localize to these very discrete points, and what makes them special? So this turns out to be a theorem by a Russian mathematician from the 70s known as Belly's theorem. And it turns out these points are very special. Okay? They turn out to be arithmetic Riemann surfaces. But more importantly, they're exactly the world sheets which admit belly maps. It's great to prove the theorem about something else you coined. Right? So what are these belly maps? These belly maps turn out to be very particular covering maps of a sphere branched over exactly 3 points. Okay? So it's going to turn out, so what am I trying to accomplish right now? I'm trying to tell you why, if you want, we should expect this particular SL2R mod U1 theory as the closed string dual. Okay? So what is the sort of information that you need to know why this is kind of interesting is that it was shown that this theory localizes to these covering maps of a sphere, of an S2. And in particular, this theory and the correlators that we're looking at localize to exactly these so-called belly maps. these covering maps of a sphere in which the world sheet wraps around the sphere. And it wraps around the sphere in such a way that it's branched only 3 over 3 points, otherwise unbranched. Okay. So in the remaining 5 minutes of my talk, I want to show you how the Feynman diagrams are even smart enough to know about this map. So that the sum over the Feynman diagrams is not just a sum over these points, but it's really a sum of world sheets embedded in this target space sphere. Okay? So let's try to see how that's going to be done. Okay? So we, from the diagram, reconstructed the world sheet. And now from the diagram, I want to reconstruct the embedding map of that world sheet into the target space. So far, is the rationale clear? So this, so maybe we'll start directly with the map. So the target space is going to be the Riemann sphere, CP1, which maybe you might prefer this drawing. But with artistic liberties here, I've drawn as a line. Okay? And the north and the south pole, at say x equals to 0 and x equals infinity, are these 2 points. And there's a third point, let's call it x equals to 1, which I've denoted here. So what is in this color? This color is about a world sheet which wraps this target space sphere 4 times. Okay? That's what this 1, 2, 3, and 4 are. And if you're a little ant, say, living on the top cover of the world sheet, what branching means is if you walk around, right when you're sitting above x equals to 0, you'd all of a sudden come out on the second sheet. Okay? And for example, now you'd come out on the 4th sheet, and then you'd come out on the 1st sheet. So there's a way of describing these maps, if you want, purely in terms of combinatorial data of permutations. It just needs to tell you 1 goes to 2, 2 goes to 4, 4 goes to 1. Okay. So now what I want to do in this remaining 2 minutes is extract that combinatorial data directly from the Feynman diagrams. Okay? How do we see this map, the way the world sheet wraps this target space from the Feynman diagram? So this is a bit of black magic. These go back to something that Grothendieck thought about, known as child's drawings, and he certainly wasn't thinking about gauge theories at the time. But this, if you want, they thought of the Feynman diagrams just as a mnemonic, a way of writing down these maps very succinctly. So let me kind of tell you how it works. So it's the same Feynman diagram, and we're going to pick some orientation. You have a question?
Maybe before. Yeah, just to clarify the. Yeah. So the graph, you assigned to it some 2D Riemann surface.
Yes.
That is going to be some point in this moduli space.
That's exactly one of these points. Yeah, let me
exactly one point.
Put it in blue. Yep.
What's the role of the covering surfaces now at this point?
So now that's just telling you about the world sheet, right? But a string theory is more than the world sheet. It's telling you about the embedding of the world sheet in the target space.
Okay.
So now what I need to do is I need to extract this A model. The A model is a sum of targets, sum of maps, right? It turns out an A model topological string is a sum of holomorphic maps. So what I'm doing right now is I'm deriving a holomorphic map, which is going to be exactly the maps onto which this theory localizes, directly from the diagram.
That will take one of these points, and map it into
Exactly.
So this map called SSO.
Exactly. So it's going to take this world sheet, and it's going to wrap this Riemann sphere 4 times, and it's going to wrap it in such a way that it's branched over exactly 3 points.
Oh, okay. Perfect.
Yeah. Great. Thank you for the question. I'm sure that wasn't clear to most people, so I'm glad you asked. Okay. So how are we going to describe this map from the Feynman diagram? So let's pick any vertex you want. I like this vertex, okay? So we assign some orientation. Let's say m goes to k, and we draw a number on the right. Okay, and we're just going to walk around this diagram. So we have 1, and then 2, 3, and 4. Okay, I've just assigned this. The 3 permutations have very nice graphical meaning because they're going to be associated to the 2 types of vertices, k and m, and the faces. Okay, so they're very natural from the diagram perspective. So how am I going to write down some permutation from this diagram? So let's start over here. Okay, so let's start with a k vertex. I go around clockwise. Okay, so this is a 1-2 cycle. And that's going to tell me that when I'm a little ant, I go on the first sheet and the second sheet get permuted. Okay, that's what this 1-2 means. And similarly here, 3-4. So I've done the k vertices. I can do the same thing now for the faces. So I go around here, 2-4 and 1-3. That's what I've written down here. And then finally, this M vertex corresponds to the M vertices. Okay, so we have 2, 3, and 1, 4. So from the diagram, I write down these permutations. These permutations uniquely specify the map. Okay, is that clear? So I've got 1 minute left. So in the remaining 1 minute, what I want to tell you is how these two pictures are related, because they probably seem very, very disconnected. So I want to tell you that I'm going to understand how every little patch of the world sheet, in fact, is embedded. And then the way that we glue the patches together and compose that with that simple map gives us this branched cover. Okay? So let's again focus our attention on one edge of the Feynman diagram, which again was just one sort of strip, 1/4 of this world sheet. Okay? So that same edge I've drawn over here for your convenience. Okay? And this edge we're going to map to an infinite strip. Okay? And it has some z coordinates. So the k vertex lives at z plus I infinity, the m vertex at minus I infinity, and the faces at 0 and 1. Okay? What I'm going to do is I'm going to take this strip and I'm essentially just going to wrap it around this sphere. So I infinity goes up here, minus I infinity goes down here, and I just wrap it around. Okay? And this map, in fact, is very simple to write. E to the I, 2 pi I z. So it's a holomorphic map. And now if you want, what you do is that for every edge of the Feynman diagram, you map it into the target space. And then you compose it with this Strabel gluing, okay? Gluing these various strips together. And the composition of this simple map with that gluing gives you exactly this branched cover. Okay. So if you want, we have a totally microscopic understanding as to how these Feynman diagrams are reconstructing the world sheet and the dual string theory. Okay. So I'll maybe just close by saying that this is somewhat embedded in a topological subsector of n equals 4. And some of the things we're working on is trying to generalize this story to the 2D chiral algebra of n equals 4. So there's the story of twisted holography there. So can we have some sort of world sheet Feynman diagram, Hooft-like picture of the twisted holography correspondence? And yeah, we're making some progress, but we've still got some work with Matthias. Okay, good. I'll stop here. Thank you very much.
Can you say again what the Belly theorem was?
Yes. So the Belly theorem is about so these type of maps are special, but you could imagine maybe any Riemann surface can sort of be wrapped around the sphere in exactly this way. But that turns out to not be true. Only very, very special world sheets can be wrapped around the sphere, branched over exactly 3 points. And you can ask which ones.
Special points in moduli space.
Special points in moduli space, so very particular Riemann surfaces. And the question is, which ones are they? Well, they're exactly these points labeled by integers. So if you want, that had to be true, but this is a sort of very nice consistency of this whole story. Okay? That somehow we know that this SL2R theory localizes to these maps. These maps only exist for these world sheets, and these world sheets are exactly the ones that we reconstruct from the Feynman diagrams. So in that
Is there a
sense,
formula which tells you how many maps there are?
well, in fact, that's basically what these correlators do. So if you want, a simple way to compute it is via the matrix model.
I see.
And the matrix model correlators, if you want one interpretation for them, is just summing over these maps, counting these maps. So that's how mathematicians use these graphs. So they just try to count graphs as a way of counting these special maps. But, yeah.
How does that formula grow with
Well, with what? With like
the genus, for example?
So genus and n, it's usually polynomial in the powers here, and the maximal power of the polynomial is set by the dimension of the moduli space. So something like
That goes factorial.
the sum of those to, I think, 3g minus 3 plus n or something.
I don't know, man.
Well, yeah, I mean the sum of these powers to that power, I guess.
as far as I understood, one such diagram corresponds to one surface, yes?
Yes.
And do you have a precise formula from these permutations to calculate the genus? Is there a nice formula to calculate the genus of this surface?
So the genus is just V minus E plus F. That's just the genus of the
Suppose I give you just this, a sequence of permutations.
the Riemann-Roch theorem.
Huh?
Riemann-Roch theorem.
Riemann-Roch
So you
theorem.
know about the degree of the cover and the number of branchings.
Say, if you want to know the moduli of this surface, say you have a torus topology and you want to know what is tau for this torus, do you have a precise formula?
Yes.
for these permutations?
Well, the map between these lengths and the moduli is a little hard. That turns out to often involve some transcendental equations.
You don't have an explicit formula.
Yeah, often no. But I would just say that, tau is one particular way of parameterizing the torus, and you could alternatively use the lengths of these Strabel graphs. Those are just different coordinates on moduli space, and it turns out these are much more.
But to really calculate tau, it's tough probably.
That's very tough, yeah.
Yeah, but this works for any genus, whereas
No, I understand.
G equals 1 is easy.
I perfectly understand. The question is about general
Yes, yes,
moduli,
yes,
at least for torus.
yes.
Is there any
This is one way of describing the moduli.
physics in this model?
Smart way of doing it.
In G, you mean in N? Something like.
Oh, yeah, in G.
Right. So everything I'm saying here is to all orders in 1 over n.
Right.
And so to that asymptotic series, you'll have e to the minus n corrections.
Right.
Those e to the minus n corrections correspond to open string in the bulk, if you want. So this closed string theory doesn't know about it. But maybe there's some way of, once you understand this closed string theory, thinking about the d-brane boundary
Yeah,
conditions in it,
that's what I meant.
and trying to replicate some e to the minus n effects.
Yeah.
So, along the lines of what people have been doing in C equals 1, that you could identify instantons, d-instantons in this theory with basically e to the minus n effects in this matrix model. That'd be great.
What if you do allow yourself to consider mixed operators like trace k cube m to the fifth
Yeah.
under
So,
one trace?
yeah. The answer is that this worldsheet theory does not know about those operators. So,
But from the point of view of this model, there doesn't seem to be something so weird about it.
I agree. I have
But they're
two
not covered by
speculations.
this Belli theorem.
They're not covered by this Belli theorem. So maybe one thing I didn't emphasize enough is that the single traces of M and the single traces of K are basically describing the branching around infinity and 0. When you have these mixed words, I can offer some speculations. In C equals 1, we think maybe they have some sort of vortex winding description.
That's what I was going to ask, where the winding.
Yes, exactly. So this somehow only knows about the tachyon momentum operators. And that's something we've been trying to work out a little with Shoda about some possible 4-matrix description, where each single trace of the matrices corresponds to both momentum and winding. And there's a sort of graph duality on the world sheet that sort of would exchange, would be like T-duality at the level of the world sheet theory. Yeah, it would be great to discuss that. We've been a little stuck. Yeah, please. We have an hour coffee break, so there's plenty of time for questions.
It seems you said something at the beginning that you try to map chiral primary correlators of chiral primaries in n equals 4 to this kind of picture. Yes, that's true.
Yes.
And how far are you in this picture from LLM geometry? Can you capture anything of it?
Yeah, geometrically sort of nowhere in a sense. What this matrix model turns out to compute are multi-trace two-point functions in the chiral algebra. So traces of k and traces of m turn out to be, so if you want this sphere, you should identify it as the sphere on which the chiral algebra of n equals 4 lives. This is very much the same way it's like where the symmetric orbifold lives. It's the boundary of this ADS3. I don't know. How familiar with the twisted holography? Maybe not. But okay, short story is that what these are computing are just multi-trace two-point functions. That we've made precise.
In a few days, we'll issue a paper with Pedro Vieira and Harish Morale, where we sort of compute this kind of correlators for chiral primaries.
Okay, great.
Like clearly, it's very similar, the setup, and
Okay, great.
they're certainly related to.
Yeah, maybe you can explain to me. Yeah, that'd be great.
This last question from Jifin. Okay. Yeah. So was there something special about the target space being CP1 with 3 punctures? Is there a similar theorem for different number of punctures or higher genus?
So different number of punctures seems to require more matrices. Okay, so we have 2 matrices. That's essentially given us this 0 and infinity. And multiple punctures also seems to get rid of this cosine. So it seems that the theorem of just covering maps with multiple points, branch covers, that we already know is exactly what this SL2R at level 1 does for a living. It computes exactly the number of maps branched over multiple points.
So what about higher genus target spaces?
That I have no idea. Okay. That will require a completely different worldsheet theory, and that's not what comes out of this.
So, yes, from the construction I understood, you have a ribbon graph, map it to some Riemann surface, and then map it to some embedding into some target space. What information besides like this map that maps into target space, like a worldsheet theory would have, I don't know, can you compute a correlator and the worldsheet together?
So that was the main result that I didn't really discuss so much, but I mean, the main result is that every observable to all orders in 1 over n, I can tell you exactly what correlator to compute on the worldsheet.
Okay, perfect.
So over here, what this corresponds to is a 4-point function of these particular vertex operators inserted at x equals infinity and x equals to 0. This third permutation is quite subtle, and this is some of the details we've been working out with Matthias. They turn out to involve, if you want, field-identified versions of the identity. And you need to sum over all degenerate representations of the identity, and that ends up recreating this third point. But that's very special to the coset.
Okay. Second question, at some point there must have been a choice because you mentioned 3 theories, and
Yes.
you only now got the A model
You
one.
only gave me 30 minutes.
Is there a way to pinpoint where that choice was made?
So the reason I discussed the A model today is because each of these descriptions has a sort of natural derivation. So I picked one particular perspective on the derivation today, which was via the Feynman diagrams. So if you want, this one somehow naturally picks out the Feynman diagrams. This B model has a very natural interpretation in terms of in what's in matrix model literature known as topological recursion. So maybe if you've seen some talks on the Virasoro minimal string, you see that this is often one of the tools they use to try to identify what it's computing. And in particular, what we have here is an operator dictionary between trace m to the k and some cohomology classes on MGN. That's, cycle. Not very helpful, but at least that's kind of the natural description that comes out of here. The equivalence to C equals 1 came via what we've dubbed open, closed, open triality, which, if you want, extends the notion of gauge string duality to saying there might be 2 gauge theories dual to the same closed string theory. And the 2 open descriptions in this case is going to be one matrix model dual to another matrix model. And that matrix model was known in the 90s in the C equals 1 literature as what's known as the Mbimbo-Muki matrix model. And it was shown via some integrability arguments, in fact, to compute correlation functions of these tachyon momentum operators. So 3 very, very different derivations of this gauge string duality that somehow naturally fall onto one formulation of the closed string worldsheet theory.
And one last question that maybe it was related to what they asked, but other operators, like Mazenc's determinants, can you add fundamentals, and how does that map geometrically?
So you mean something like determinant insertions?
Yes.
Yeah, so determinant insertions correspond to brain insertions in this theory. In the chiral algebra, they correspond very clearly to these brains that were computed by Davide and Cassia. So you can literally find the shape. And they're basically giant gravitons in this chiral algebra subsector.
And in this, does that fit within this story?
Right. So if you want this worldsheet theory, you should think of as the mirror symmetric theory to the B model description of twisted holography.
just to check if I understand correctly, if you had started with another Feynman diagram, you would get covering maps of a sphere with more branch points? Or?
No, always 3 branch points. What ends up changing is just the behavior around, the branching around each of the 3 points. So there's always 3 points because there's 2 types of vertices and 1 type of face. So that specifies the total number of branches.
And the theory is always this SL2R.
It's this SL2R mod U1. And in fact, actually, what's kind of even quite cute is that each degenerate representation of the identity of the vacuum, so this is spectral flow of the vacuum, 0, 0 state, ends up being exactly 1 Feynman diagram. So the sum over Feynman diagrams is a sum over all the degenerate representations of the vacuum. So the world sheet really exactly mimics what the open string design wants to do.
Okay.
People deserve a break here.
Okay, so let's have a break. So let's.
Thank you.